At the heart of organic chemistry is the carbon atom. So understanding its atomic structure and bonding is crucial to grasping the wide variety of organic compounds. Carbon is element number 6 in the periodic table, meaning it has 6 electrons in total. The first 2 electrons are in the first electron shell, and the last 4 electrons are in the second shell. The first electron shell has one subshell, that is the 1s subshell, where the first 2 electrons are found, while the second shell, where the 4 valence electrons are found, has 2 subshells, that is the 2s and 2p subshells. So the ground state electronic configuration of carbon is 1s2, 2s2, and 2p2. Meaning its valence electrons are in the 2s and 2p orbitals. Now here is where it gets interesting. Carbon's ability to form so many different compounds comes from a concept called hybridization. This is the mixing of orbitals to form new hybrid orbitals. Depending on the types of bonds carbon forms, it can hybridize in 3 ways. Either sp3, sp2, or sp hybrid orbitals. To start, carbon's ground state configuration, as stated earlier, is 1s2, 2s2, and 2p2. But there are 3 available 2p orbitals, which are 2px, 2py, and 2pz. So for the 2p2 orbital, the 2 electrons occupy 2 of the 3 available 2p orbitals. That is the 2px and 2py. Thereby leaving the 2pz orbital empty. This means that the actual ground state configuration of carbon is shown as 1s2, 2s2, 2px1, 2py1, and 2pz0. But in organic chemistry, we ignore the 1s subshell and focus only on the 2s and 2p subshells, where the valence electrons are found. Normally, only 2 of these 2p orbitals, that is 2px and 2py, have unpaired electrons, which would limit carbon to forming just 2 bonds. So to form more bonds, carbon promotes one of its 2s electrons to the empty 2p orbital, specifically the 2pz. This results in 4 unpaired electrons. This new state of carbon is what is known as the excited state, with the valence electron configuration as 1s2, 2px1, 2py1, and 2pz1. This allows carbon to undergo hybridization, creating new orbitals with unique shapes and bond angles. As stated earlier, depending on the types of bonds carbon forms, it can hybridize in 3 ways, either sp3, sp2, or sp hybrid orbitals. In sp3 hybridization, the 2s orbital mixes with all the 3 2p orbitals, 2px, 2py, and 2pz, to form 4 equivalent sp3 hybrid orbitals. And these new orbitals are actually degenerate, meaning they have the same energy. They are arranged in a tetrahedral shape with a bond angle of 109.5. And this allows carbon to form 4 sigma bonds, as seen in methane. For sp2 hybridization, the 2s orbital combines with 2 of the 2p orbitals, specifically the 2px and 2py. This forms 3 equivalent sp2 hybrid orbitals, and the remaining 2pz orbital stays unhybridized and is used to form pi bond. The 3 sp2 orbitals are actually degenerate and are arranged in a trigonal planar shape with bond angles of 120 degrees. This type of hybridization is seen in ethene, and the unhybridized 2pz orbital of each of the carbon that forms ethene overlap, creating a double bond, which is specifically a pi bond. In sp hybridization, however, the 2s orbital mixes with only one of the 2pz orbital, specifically the 2px, to form 2 equivalent sp hybrid orbitals. The other 2 of the 2p orbitals, which are the 2py and 2pz, remain unhybridized. The resulting sp orbitals are degenerate and align linearly, creating a bond angle of 180 degrees. And this kind of hybridization is seen in ethane, where each carbon atom uses one of the sp orbitals to form a sigma bond and the two unhybridized p orbitals to form two pi bonds, resulting in a triple bond. So in summary, hybridization in carbon actually involves the mixing of its s and p orbitals to form new orbitals that shape its versatile bonding pattern. This adaptability allows carbon to form millions of different compounds, making it the backbone of organic chemistry. And understanding these bonds is key to exploring the behavior and reactivity of organic molecules. In our next video, we'll talk about the classification of organic compounds and the functional group that various organic compounds have. So this video is actually the first part of our introduction to organic chemistry. In our second part, we will discuss the topics just mentioned. Thank you very much for tuning in to this lesson on Introduction to Organic Chemistry. If you find this video interesting and helpful, hit the like button, leave a comment, and subscribe to our channel. See you in our next lesson.